Hi, before you watch this video, make sure you watch the video on assembly line balancing, which gives you a lot of details and kind of sets you up for this second video. All right. And here is another example that we will do. In this example, they have given various tasks that must be completed, and task times are given. If you add up all the task times, you will see that they add up to 509 seconds. And I have also drawn the precedence diagram, which is again explained in previous video. So now we are ready to answer some questions. They are asking us, what is the longest possible cycle time? Longest possible cycle time or takt time, if you have just one station and one guy doing all the job, he will take or she will take 509 seconds. So the longest possible cycle time is 509 seconds. Beyond that, it doesn't make sense because the worker will be done and he has to move on to next task, next unit. So the longest possible time is 509 seconds. What is the shortest cycle time, especially if you can't split a task, you can't have parallel stations, then the shortest time that you can potentially have is the smallest number you can find, which is this one. The largest number you can find, which is C takes the longest, 75 seconds. So you're given that you can split a task, you must have several stations, each taking 75 seconds. And you really need 7 stations. You know why? Because 7 stations. Because 509, the total work that you have to do, divided into 7 by 75. So you will have several stations all doing 75-second worth of work to make 1 unit. So that will be 6 point something, and you have to round it up to 7. So 7 is the number of stations you will need, but the shortest cycle time will be 75 seconds. Now, suppose the production goal is 200 organs per 8-hour shift. So what is the theoretically minimum number of station? You will also need to know the cycle time. Cycle time, the problem has not specifically asked, but you have to calculate cycle time. So cycle time. So basically, in 8 hours, you will make 200 items. So divide 8 hours by 200. And since task times are in seconds, so you have to convert this into seconds. 8 times 60 times 60 seconds divided by 200, and that number will be 144 seconds. Now, if you have to do all the 509-second worth of task in 144 seconds, you must divide the 509 task into several stations, each requiring 144 seconds. So how many stations you will need? Well, number of stations you will need theoretically is 509 divided by 144. Again, this is explained more beautifully in the previous slide, previous video. 509 divided by 144 will give you 3.53. And even if it is 3.01, you have to round up to 4. So you will need 4 stations. So minimum number of stations you will need is theoretically 4 stations, 4. And cycle time is, we just calculated 144 seconds. So you have to make 1 unit every 144 seconds so that you can make 200 units in 8 hours. Okay. Now, we have to use the longest operation time heuristic to allocate tasks to various stations. All right, so let's go to next page. Longest operation time heuristic. All right. So we know the cycle time is 144. And we know that you will need at least 4 stations. Who knows? You might need more because of inefficiencies. All right, so let's begin. You have 3 tasks which are ready for allocation. You cannot do D, E, etc., but The three ready tasks are A, B, C. And we are using longest operation time. So of A, B, and C, task C takes the longest, 75 seconds, and each station gets 144 seconds. So 144 minus 75 will give you 69 seconds. And after you are done with C, the only task you can do are A and B. You can't do K. So A and B are the only tasks. And of A and B, B takes the longest, 55 seconds. So allocate task B next, and time remaining 14. And after you are done with B, you can potentially do A, E, and F. A, E, and F. Of A, E, and F, which one takes the longest? 40 seconds. By the way, you have 14 seconds left. There's no task which, well, I takes 14 seconds, but I is not ready for allocation. So you can't bend the rule. You can't plug it I in this station, because for doing I, you must complete G and H first. So anyway, so the only tasks already are A, E, and F. So of A, E, and F, let's go with A. That takes the longest. Task A, 40 seconds, time remaining 104. And after you do E, task D, E, and F already. D, E, and F. Of D, E, and F, D takes the longest, 40 seconds, time remaining 64. And after you do D, the only task which you can do are E and F, not G. G is not ready yet, because you're not done with E. So of E and F, F takes the longest. So allocate F here, 35 seconds, time remaining 29. And after you do F, the tasks which are ready are E and H. And neither of these tasks will fit in this station. So you will be wasting 29 seconds. So you have to go to next station and allocate E and H. So H takes the longest. Allocate H here, takes 70 seconds, time remaining 74. After you do H, tasks which are ready is just E. That's it. And how long does E take? E takes 30 seconds, time remaining 44. And after you do E, the task which is ready is G. And G takes 45 seconds, and it won't fit in this station. So this 44 seconds will be wasted. So you have to go to next station and allocate task G, takes 45 seconds, time remaining 99. Again, every station gets 144 seconds. So when you allocate G here, after G, the task ready is I. Allocate I, takes 14 seconds, time remaining 85. And after you do I, you can do J. J takes 65 seconds, time remaining 20. And then K opens up. Unfortunately, because you're wasting so much time at various stations, you will need more than 4, the minimum number that we calculated. That was theoretically minimum, but realistically, we see that you will end up with 1 extra stations, time remaining 104, and you're done. And again, you're wasting a lot of time. I'm going to show you quick calculation. How do you calculate efficiency? You're wasting 14 seconds. So out of 144 seconds, you're wasting 14 seconds. So you're really working for 130 seconds divided by 144. So 130 as a ratio of 144 times 100. And similarly, you can do the calculation for each station. By the way, the line efficiency for the whole line efficiency is simply, you know that you're doing 509 seconds worth of work. You did this addition before. You add up all the task time, that's 509 seconds. And to do this, you are actually needing 5 stations, each requiring 144 seconds. And that will be the line efficiency. There is something known as line imbalance, so that will be simply 100 minus, if this is whatever percentage is, the 1 minus that number, 100% minus that whatever time is efficiency is the imbalance percentage. Okay. All right, so we did this one using longest operation time heuristic. Now we are going to do the same problem, but using a different heuristic. And this time the heuristic is most following task first. So I counted all the tasks that follow A. Task A has 1, 2, 3, 4, 5, 6 tasks following A. B has 1, 2, 3, 4, 5, 6, 7. So 7 tasks follow B. You cannot do those 7 tasks without A, and so on. All right, given this information, we are ready for following the most following task heuristic. And there's a typo here, TAS, task heuristic. Okay. All right, so again, to begin with, you have same A, B, C that are ready of A, B, and C, which has the largest number of following tasks, looks like B. So you will allocate B first. How long does B take? 55 seconds. And time remaining will be 89. That is, again, cycle time is 144 seconds. So 144 minus 55 will give you 89. You're done with B. What's available? What can you do? It looks like you can do A, you can do C, and you can do F. That's it. You can't do D and E. So of A, C, and F, which one has the largest number of following tasks? Looks like A. So A has 6 following tasks. How long does A take? It takes 40 seconds. Time remaining 49. And after you do task A, oh, sorry, it moved. Okay. A, you have task C, D, E, and F. They're all open, available now for allocation. And of the C, D, E, F, which one has the highest number of following tasks? It looks like D, E, F take all of them. Take 4. They have 4 following tasks. So there's a tie. Generally, you break the tie using the longest operation time. So if you look at D, E, and F, D takes the longest, so you will allocate D first, takes 40 seconds, time remaining 9. And after you do D, the tasks which are available are C, E, and F. Of C, E, and F, there's again two-way tie, but anyway, you have 9 seconds, nothing will fit here. You go to station number 2, and E and F, E and F, they both have 4. You break the tie by longest operation time. F will go first, 35 seconds, time remaining 109. And after you do F, the tasks which are ready are C, E, and H, C, E, and H. And which one has the largest number of following tasks? C has 1, E has 4, so E will be next. And E takes 30 seconds, time remaining 79. And after you do E, tasks which are ready are C, G, and H. And C is has 1 task, G has 3, and H has 3. So you break the tie by allocating task which takes the longest. H takes the longest of E and G. So H will go here, 70 seconds, time remaining 9. And after you do H, you have tasks C and G available. So you go to next station, 9 seconds is not, you can't fit in anything. G takes 45 seconds, and G has the highest, G is the highest number of following tasks, 45 seconds, time remaining 99. And after you do G, tasks which are ready are C and I will go next because it has 2 following tasks. So 14 seconds, time remaining 85. And after you do I, C, and J are available. C and J, they both have 1 following task, C and J. So you break the tie by allocating C because that takes longer. 75 seconds, time remaining 10. And then you can do J. So you go to next station, J takes 65 seconds, and time remaining will be 35 plus 45, 79 seconds. And then you have K. K takes 40 seconds, time remaining 39, and you're done. And you can calculate efficiency, which I explained earlier. Obviously, this is much better allocation. Previous time we needed 5 stations. And this particular case, we need 4. Now, can you conclude from this example that both following heuristic is better? Not really, not really. In fact, in general, this is a superior heuristic. But remember, this is called heuristic because in some case situation, this might work better than this one and vice versa. Okay, that's why you have to keep trying. All right. Now I'm going to talk about the third heuristic, which is greatest positional weight, which is simply all the tasks. So for A, the weight is going to be A, and all the tasks that follow B, add up their times. Add up time for A as well as all the following tasks. And I've done this one, and I got these numbers here. Okay. And then based on that, I put them in the order of greatest positional weight. Obviously, A has the highest positional weight, 354. No, I'm sorry, that's B. B has the highest positional weight. So B is number one, A is number two, F is 224, C, and so on. So this is arranged according to greatest positional weight. All right, so we are ready for trying this method out. Excuse me, it remains the same. A, B, C are ready, and A, B, C, it looks like B has the highest position, so B takes 55 seconds, time remaining 89, and after you do B, tasks which can be done are A, C, and F. A, C, A has a second highest. A takes, how long does it take? 40 seconds, time remaining 49. And after you do A, tasks which can be done are C, D, E, F. So C, D, E, F. F has the highest positional weight. So we will allocate F here. How long does F take? F takes 35 seconds. Time remaining 14. And after you do F, tasks which are ready are C, D, and E. C, D, and E. So D is the next one. D, how long does D take? 40. So you go to next station, D takes 40 seconds, time remaining 104. Every station gets 104 seconds. And after you do D, which tasks are available? C is available, E was already available, and H is also available. So after you did F, I forgot to put H here. But H should not, H is lower up, so it should not affect any answer. C, E, and H are available. C, E, and H, which one has the highest position? C, E, and H. So E is the highest. E is higher in this number. So, E will be next one. How long does E take? 30 seconds, time remaining 74. And after you are done with E, tasks which are available are C, G, H, C. So H, it looks like is high up there. H, C, G. Okay. So H will go next. How long does H take? 70 seconds. Time remaining 4. And after H, the tasks which are open are C and G only. C and G, C and G. So C is higher. So C will go next. How long does C take? 75 seconds. Time remaining 69. And after you do C, the task which is available is only G is available. And so you will go with G. Anyway, G takes 45. Time remaining 14. And after G, you can do I. And wow, I will fit here beautifully, time remaining 0. And then you have J. So you go to next station. J is 65, time remaining 79, excuse me, 79. And K takes 40, time remaining 39, and you're done. So even this method gives you the same allocation, but slightly different order. It's BAF, here it was BAD, and so on. But this was also able to do it in 4 stations. So hope this explains to you these three different heuristics. Okay, good luck with it. Stop recording.